So now we've discussed comparators, but there's one problem that one can get with a comparator circuit, especially if the input that we have has a lot of noise or a lot of random fluctuations on it. So let's see what I mean by that. So suppose we are looking at this sine wave to square wave converter that we've been looking at. And let's take the old simple example where the trip point was 0 volts itself. Okay, so the circuit will look something like this. So the trip point is 0. Whenever your sine wave crosses 0 volts, your output will change state from plus Vsat to minus Vsat or minus Vsat to plus Vsat. So here is the input, but sometimes what happens is that your input voltage is not smooth. There are some small fluctuations on it. So what we are calling a sine wave over here might actually be something like this. I'm exaggerating the amount of fluctuation on it, but that's what I mean. In principle, there could be some noise riding over your sine wave. Or if you want me to zoom in on this part, it might look something like this. So here is your 0 volts, and we expect that the sine wave is coming down like this, but actually it isn't. It might have some small wiggle, some fluctuations on it. Now what happens when you pass this through a comparator circuit? All hell will break loose, because you see it is crossing 0 over here, then over here, then over here. So your output might look kind of like this. Because every time your noise crosses 0, your output state will change. And this can be disastrous, because presumably this output is going somewhere to run some other circuit. And then that circuit will quickly keep turning on, off, on, off, on, off. That can't be good. You might not want that from a physical point of view. It might even be harmful for your circuit to keep switching on and off so fast. So we don't want this kind of problem. So we have to introduce a variation of the comparator, and that variation is called the Schmitt trigger. So let's see what the Schmitt trigger does. A Schmitt trigger is nothing but a comparator with the added positive feedback. So the circuit looks like this. And let's call them R1 and R2. So now you see this reference voltage over here is, well, before I do that, so because there is a feedback, I can define what is called the feedback fraction. So V ref is just, because if you look at this circuit over here, this is just a voltage divider. So Vref is V out times R1 divided by R1 plus R2. So I call this the feedback fraction. I think we have discussed feedback fraction in the last lecture or the one before that. Or so from here we just say that Vref is just B times V out. So every time the input voltage is going to be compared to this reference output voltage. So now let's try and analyze what happens in this circuit. So suppose our output voltage is currently at positive saturation. So then the reference voltage will be plus B times Vsat. So that means our tripping point happens when Vin increases beyond beta Vsat. Okay. Now, once Vin goes beyond B Vsat, remember Vin is at the negative terminal. So now your output switches to the negative Vsat state. So now V out is at minus Vsat. So what happens is that the Vref has changed now. Now Vref is minus B Vsat. Earlier, our reference voltage was always some fixed number. Either it was 0 or by putting that extra voltage divider over there, we had changed the reference voltage. But still, it was fixed. Now, your reference voltage changes depending on what is your output. So, when your output is plus Vsat, reference voltage is positive. When your output is minus Vsat, your reference voltage becomes negative. So, now the trip point happens when Vin is less than minus B Vsat. And graphically, if I plot this, I get a very interesting figure. Suppose this value over here is plus B Vsat and this value over here is minus B Vsat. So initially when Vin is negative, your output is at plus Vsat. And tripping point at this stage is plus beta Vsat, plus B Vsat. So it's not going to trip until it comes here, and then it will trip. However, now that we are at minus Vsat, now that we are over here, if I start to decrease the voltage, now I'm here at minus Vsat, and the tripping point is now not plus B Vsat but minus B Vsat. So now if I start to decrease the voltage from here, I don't trip at this point, I have to come all the way back over here and then it will trip. So depending on whether I am increasing the input voltage or decreasing the input voltage, the trip point is different. When I am increasing the input voltage, my trip point is plus BVsat. When I'm decreasing the input voltage, the trip point is minus BVsat. In fact, it would have been nice if I would have used different colors. So during the increasing Vin, the input output graph looks like this. And when I'm decreasing Vin, my input output graph looks like this. So this kind of characteristic where the tripping point property depends on whether you are increasing Vin or decreasing Vin, this is called hysteresis. And not just in electronics, in general, in any branch of physics, whenever you find that the property depends on whether a certain quantity is being increased or decreased. So it depends on the direction in which your input is going. This is called hysteresis. You will, for example, also find hysteresis examples when you're studying magnetism. So the terminology that we use over here is that the upper trip point and the lower trip point are different. So the upper trip point, or what we call a UTP, is plus BVsat, and the lower trip point, or the LTP, is minus BVsat. And because these two are different, you get hysteresis. What we had on the previous page over here, this is the inverting Schmidt trigger, because your input is going here to the inverting terminal. You can also have a non-inverting Schmidt trigger. So now you can see that Vin is going to be R1 over R2 times V out. And so now when V out is at plus Vsat, your trip happens when V in is less, when Vn is equal to minus R1 by R2 Vsat, right? But in the other direction, so when V out is negative Vsat, then the trip will happen when Vn is plus R1 by R2 Vsat. Sorry, this makes sense. So yeah, this is the negative. Vn is minus R1 by R2 V out, and that is why these are the two trip points that you get. So again, doing this graphically, when you are already at plus VSAT, then the tripping will happen for the negative one. So let's call this my minus R1 by R2 VSAT, and this point is plus R1 by R2 VSAT. So when you're at plus saturation, your tripping occurs over here. But when you are increasing, then here is how the tripping happens. So in this case, we will say that the lower trip point is minus R1 by R2 VSAT, and the upper trip point is plus R1 by R2 VSAT. What happens? Oh, first of all, we should discuss how does the Schmidt trigger solve the problem. So initially, we had the problem of there being too much noise in the system. So there were lots of wiggles on the sine wave over here, and it was to solve this problem that we introduced the Schmidt trigger. How does this solve that problem? So the Schmidt trigger will only trigger off in one direction. It won't trigger back and forth in both directions. And the property of noise is that it is not in a uniform direction. It keeps going up and down, up and down, up and down. But the Schmidt trigger will not trigger every time you go up and down. So it will trigger just once during the crossing. So that's why the Schmidt trigger is considered more efficient. Let's see what the Schmidt trigger does to a sine wave. Now, there is a UTP and there is an LTP. So this is your lower trip point. This is your upper trip point. And now, so every time when you're increasing, it will trip at the UTP. Every time when you're decreasing, it will not trip at the UTP again, it will trip at the LTP. So it looks something like this. This is your Schmidt trigger output.